Jacobian Hessian and Tensor Matrix. Okay, so we will proceed discussion in Jacobian Hessian and Tensor Matrix. Okay, so in this discussion, what we are proceeding right now, Jacobian Hessian and Tensor Matrix. Okay, so in this discussion, we are right now into the finding the something called global minima. Global minima we are finding through a way called gradient descent. This is what is the topic that we have started, and that is gradient descent. Gradient descent is considered as the best algorithm to find global minima or minima at least. What is global minima or minima at least? I believe that can be understood very clearly. Okay, so consider this is x-axis. Okay, consider this is x-axis. If this is x-axis, then there is a curve like this. Where is minima? There is no minima. Where is minima? This point is minima. Okay, from origin, if I take here, if I draw a vertical, then it is going to hit this point. So I can say at x equal to a, if this point is a, above a, this curve is at minimum distance. This to x-axis, this gap is very less, otherwise gap is more. This is the minimum. This looks like global minima, means out of all possible minima, this is global minima. There can be other minima also. Okay, there are two minima here. Okay, there are two minima here. This is minima and this point is minima. This point is minima, this point. This is called local minima. If I have something like this, then around this region, this is local minima. Makes sense? What is local minima? If I see, then I can say this is a minimum point. But this graph is continuing and there is a bigger minimum. This is called global minimum and this is called local minimum. Anyway, the concept is how to find minima is if your graph has the equation of fx. If the graph has equation of fx, then dfx by dx, setting it to 0, find the value of x. There it is minimum. Understand? Consider the graph is x square minus 2. Then dfx by x graph is x square minus 2x. Then dfx by dx will be 2x minus 2. 2x minus 2 equal to 0 means 2x equal to 2, x equal to 1. If I have a graph at x square minus 2, x square minus 2x, then at x equal to 1, we can see the minimum point. Okay, where it is not possible, if I have a graph at x to the power 3 by 3 minus 2x, if I take differentiation, it will become x square minus 2. X square minus 2 equal to 0 means x equal to plus minus a square root of 2. Plus minus a square root of 2 means we cannot find the real value of x. Square root of 2 is irrational number and we cannot find the real value of x. Either I take some calculator or whatsoever. To find the square root of 2 or to find the real number, we have to follow another way. This way is not working. How to find a minimum, local minima or global minima in a curve is if your curve equation is fx, where x can be vector, not necessarily that x will be simple x-axis. If I go in multiple variable case, this x what we are seeing along x-axis, this x what we are seeing along x-axis, this x will become a vector. Right now it is an x-axis, slowly it will become a vector. Okay, means if I have a xy plane, any point on xy plane will be called x vector. Any point on x-axis will be called x vector. But vector is not required if it is single dimension. Why vector is not required when it is single dimension? Okay, the big reason is that there is only one I vector. There are not two I vector. If there are two I vector, then we can say that, okay, if there are two vectors, then we can say vector is required. Means if there is a x-axis, y-axis, z-axis, where we have x-axis and y-axis as independent and z-axis is dependent. If that is the case, then this xy plane is called independent vector. Any point on xy plane can have two components. Understandable? If I say this as my xy plane, this is x-axis, this is y-axis. Any point on xy plane has two components, along x-axis, along y-axis. Means if I have a point here, then since this point has two components, consider this point is x, then this is x1, this is x2. I can write x as x1 as its x component and x2 as its y component. What is your x on xy plane? The x on xy plane is x1 is x1. Okay, okay, someone can ask where you stay. Where you stay? I stay something like near to that school. Okay, okay, if you go north from the particular school, some kind of 1 kilometer exactly, no, you know that school, right? Yeah, I know that school. From a school you just go, from school you just go 1 kilometer north around. Okay, if it is difficult for you, then you know there is a post office. Yeah, I know. From there you go eastward half kilometer. Means there I stay. It is something like that. If I have a xy plane, this is y-axis, this is x-axis, and this is origin, then I have a point here called x. X has x1 component. Means if there is a school here, then from school it is at this distance. Makes sense. Okay. Or this has this much as y component. Means something like that. If there is, I believe that is other way. If this is eastward and this is northward, then there is a school here. From a school it is x2 distance northward. Makes sense? If there is a post office here, then sorry, yeah, if there is a post office here, then x1 distance from the post office. So if there is any point on xy plane, then I can say from origin along x-axis how far it is, from origin along y-axis how far it is. So any point can be represented as a component, what component you have along x-axis, what component you have along y-axis. Okay, if I say that from the school, where I stay from the school, it is 1 kilometer north, then that can be called as J component. And from the post office, it is half kilometer east, then that will be called as I component. I stay, if someone takes this measurement, then I can say I stay at 1 by 2 I plus 1 J. Okay, if someone finds origin in between the school and post office, then this is how I stay. Everybody understandable? Anyway, so if I am talking about any point on x-axis as x or a, that can be represented as same x or a in multiple variable case, but it will become a vector. Anyway, now what is technology to find the minimum point on any curve through an algorithm? One algorithm is, if your curve is fx, f in bracket x bracket close, x can be vector. If this is dual independent variable case, if independent variable, what we are talking, that is xy plane, dual independent variable means nowadays it is called dual input also. Means x-axis and y-axis, these two are input and z-axis is the output. Understandable? Okay, means generally what people study in the book, dy by dx, dy by dx, d2y by dx square, it is called single input function, where x is only independent component and y or function over x is the dependent component. There can be two independent components, x and y, or it can be said as that there are two input x and y. Means if I have xy plane, then x and y as independent, and dependent is the z-axis. I believe it is understandable. Z-axis is called function over x comma y. What is x comma y? What is x comma y? If I take this as xy plane, this is x-axis, this is y-axis. If I take this as xy plane, this is x-axis and this is y-axis. In that manner, if I take any point here, this can be represented as x comma y or x vector. From origin, if I draw a line, this will become x vector or x comma y. Someone will say, I will say a vector. You can say a vector. There is no problem. What the main concept is, any point on this xy plane can be represented by a single point called ax whatsoever. Not required I have to say x comma y. Not required. Just a. If I say a, then a is vector. If I just say it is a, then a is vector. If I say x comma y, then it is coordinate. Two things. Makes sense. If I say if I have only x-axis and this is origin, if I say I have a point here called a, then I can say ai in vector term, ai, or just a variable called a, no difference. A or ai, there is no difference. But if I am in dual variable case, where x-axis and y-axis both are independent components, and above xy plane I have a 3D shape. Above xy plane I have a 3D shape. Above xy plane I have a 3D shape. This height is called z-axis and this is called xy plane. Now if I want to represent any point on xy plane, then that point can be said as a. This point is a or x comma y. In variable it is x comma y, or as a point it can be said a. If I break a, then this is a1. If I break a, then this is a2. I can say this as a1 comma a2 or just a. Or if this is x and this is y, then x comma y. So I can represent any point in two forms. One form is vector form, that is a vector. A on top you just mention one arrow. A on top you just mention one arrow. Okay, that is called a vector. So anything can be represented either as a vector or through the variables like x comma y, anything. Now if I have a surface, if I have a xy plane, and above the xy plane if I have a surface like this, then tell me point on this xy plane. At that point the height of this is minimum, and that point is this, where the height is minimum. How to find a point on xy plane where height is minimum? And that falls in a scenario called through an what is algorithm? One algorithm, if your height at any point x comma y, if I take any arbitrary point here as x comma y, and above x comma y, if I draw a vertical line, then it will hit this point. Above the x comma y, if I draw a vertical line, it will hit this point. It will hit this point. It will hit this point, where I have variable x comma y on xy plane. From that point, if I draw a vertical line touching the x comma y on xy plane, this height is called function over x comma y. Now it is understood that what are the two ways I can describe the height. Understand? If there is a xy plane on xy plane, there is a xy plane on xy plane. This is x-axis, this is y-axis, and there is a point on xy plane called x comma y. X comma y is variable. Against each x comma y, if I draw a vertical line, it will hit this 3D shape at so many points. Okay. At each point, if I draw a line, it will go and hit the surface at any x comma y. This height is called function over x comma y. If I represent any point on xy plane with a vector called x vector, which has two components, x1, x2, or any point on xy plane as a vector, which has two components, a1, a2, or any point on xy plane as x comma y, then this height will be f in bracket x bracket close, x vector. or f in bracket a vector bracket close, f a vector. Whatever we are, the way we are representing the point on xy plane. If point on xy plane is represented as x vector, the height will, at that point, the height that is touching the surface, this height will be f in bracket x vector bracket close. If that is a vector, f in bracket a vector bracket close. If that is x comma y, then f x comma y bracket close. Okay, so this height is fx vector, fa vector, or fxy, whatsoever it is. Okay, what about this point? This point full coordinate is x vector comma fx vector, a vector comma fa vector, or x comma y comma fx comma y. Okay, fx comma y, fa vector, fx vector, all are called z also. They are denoted as z also. Understand? Now concept is what algorithm you use, that you will say that on xy plane at this point, on xy plane, if you draw a vertical line, it will hit the minimum. This height will be minimum. One algorithm is, if you consider, if point that you are representing on xy plane where the height will be minimum, and that point, if I say it is x comma y, then that height is fxy. Okay, do one thing. Calculate the change in the height 1 unit movement along x-axis, keeping y constant. That is called dfxy by dx. Calculate the change in the height along y-axis, 1 unit movement along y-axis. That is called dfxy by dy. If it is minimum, then no change will be seen along x-axis in the height. No change will be seen along y-axis in the height. What are you talking about? Consider there is a point on xy plane called x comma y. If I draw a vertical, it will hit here. If I move 1 unit along x-axis, then again I draw, it will hit another point. There is a change in the height. Means dfxy by dx, keeping y constant, there is something. But if I am at minimum, this is something where tangent is, slope is 0. If slope is 0, moving one very small distance, there is no change in the height will be seen. Here the change in height will be seen, but here no change in the height will be seen. Means, and no change in the height will be seen along x-axis and along y-axis in both directions. If that is the case, then dfxy by dx equal to 0 setting, we get one algebraic equation in x and y. Okay, dfxy by dy equal to 0, we will get one algebraic equation in x and y equal to 0. I have two independent variables, two equations to solve, and finally we get x comma y, and for that fxy is 0. Fxy is minimum. This is one algorithm to find the minimum point. dfxy by dx set it to 0, dfxy by dy set it to 0, considering change in the height along x-axis and change in the height along y-axis. At a minimum point is, there is no change in the height. So dfxy by dx will be 0 because there is no change in the height, and dfxy by dy will be 0 because there is no change in the height along y direction also. If that is the case, then what will happen? You will get the x and y for which you are seeing the minimum point. This is one scenario. We have described it by this scenario also. Sometimes you will not get x and y in a real number. This is what is expected. Then there is another algorithm called gradient descent. Gradient descent is another algorithm to find the minimum point. And what is the scenario for the gradient descent is, if this is the minimum point, then start from any other point, and from there you start traveling in a way that if I take a tangent at this point, okay, this is a tangential line. Actually, for the 3D surface, there will be a tangential plane. So if I take a tangential plane at any point, there are two directions. One direction is up and one direction is down. If I move up, then I will move toward the maximum. If I move down, then I will move toward the minimum. The slope of this tangential plane is called gradient vector, or in another way, dfxy by dx at any point how much height is changing along x-axis. This is one component of the change in the height. How dfxy by dy, how height is changing along y-axis. If both are 0, then we will get the minimum, but we are not able to get it. But at least at any point I can calculate consider this point is going down and it hitting the xy plane at a point called 2, 3. If I have fxy, consider fxy is x square plus x into y. fxy is x square plus x into y. dfxy by dx will be an equation in x and y. dfxy by dy will be equation in x comma y again. Okay, if I replace x and y with 2, 3, I get two components of the derivative. One derivative is dfxy by dx. It will come as some number if I replace x and y as 2, 3. dfxy by dy, it will come as some number if I replace x, y with 2, 3 again. If that is the case, then we will get a I component of the gradient and j component of the gradient. Understandable? I'll try again. Okay, so what I am trying again. So what I am trying again is, if this is xy plane, if I have any point at x, this is origin, this is x-axis, this is y-axis. If I have any point here as x, then there are two components called x1 and x2. Similarly, if there is a point called x here, and at this point if I draw a vertical line, and that vertical line is going to hit this surface at this point, then it has two components. This point has two components. One component, if I cut it like this, then this is called a zx plane. If I cut it like this, then this is called a zy plane. This is y-axis, this is x-axis. This is called zy plane, zx plane. Now at this point, if I go on the xy plane and I move along x-axis only, then per unit movement, how much height change I see. If I move along y-axis, per unit movement, how much change in the height I see. That is nothing but derivative only. Along x-axis, it is called dfxy by dx. Along y-axis, it is called dfxy by dy. That is the scenario. So change in the height along x-axis, change in the height along y-axis. If I had taken single independent variable, then this is x-axis and there is a curve like this. If there is a curve like this and this point there is a height called fx, if I move 1 unit, then I will hit another point. How much change in the height? I am seeing 1 unit movement. But 1 unit movement is happening only on x-axis, there is no other axis. But in xy plane, if I am trying to find at this point what is change in the height, then it has two components. One is along x-axis, what change in the height you are seeing. Along y-axis, what change in the height you are seeing. One component is called dfxy by dx. One component is called dfxy by dy. This is how we tackle the multiple variable case. We cannot say at this point what is the change. Yeah, that is called directional derivative. If I move in one direction 1 unit, then what is change in the height we see. That is called directional derivative. But for the generic term, from here if I move 1 unit, someone will say in single dimensional case dfxy by dx, tell me what is the change in the height per unit change in the length at any point x equal to x. Okay, dfxy by dx can come in algebraic equation where if you set x equal to some point, then that point will say that okay, at this point what is the height change we see if I move 1 unit. Someone will say, can you tell me similar thing in xy plane? Yeah, similar thing in xy plane if I talk, then at any point if I move 1 unit along x-axis, then what is change in the height? At this point if I move 1 unit along y-axis, then what is change in the height? Okay, means if I move from here to here, if I see the 3D shape, there will be change in the height. If I move from here to here, then change in the height. This change in the height is called dfxy by dx. This change in the height is called dfxy by dy. There are two components of the change in the height. If both components are 0, and then I am able to find the x comma y value, then we have got the minimum. But sometimes it does not happen. Consider this is the point where it is minimum. At this point, if I draw a vertical, then it is minimum. So we will start from any arbitrary point from here, and we will try to come to this point. This algorithm is called gradient descent. Just saying dfxy by dx equal to 0, dfxy by dy equal to 0, and finding the x and y. This is one coarse way, and with that way sometimes we are not able to get the x and y for which it is minimum. Okay, new technology has come that is called gradient descent. So if someone is not able to find the minimum, okay, if there are so many local minima, then it will break into so many x and y. There is no problem. But sometimes that is also not possible. So gradient descent in the algorithm, to find the point where the minimum height is there on xy plane, you start with any arbitrary point and start moving. At this point, if I start at this point, then there will be a gradient vector along. There is a derivative of this point along x-axis. There will be derivative at this point along y-axis. This derivative is called dfxy by dx. This derivative is called dfxy by dy. Means if from here, if I take the height, from there, if I take the height, the point I am talking right now, if I take the height and this is the point, then if I move 1 unit along x-axis on xy plane, then how much height is changing? If I take 1 unit along y-axis, then how much height is changing? One is called dfxy by dx and one is called dfxy by dy. Together, I can say that it is dfxy by dx I vector plus dfxy by dy j vector. If I have I vector j vector combination plus, it can be represented as vector. This vector has two components, dfxy by dx, that is a derivative, dfxy by dy, that is derivative. If I have a vector where both components are derivative, I can call it as derivative vector, or I can call it as gradient vector. So every point on xy plane, now xy plane, at every point there is a gradient where this component is dfxy by dx and this component is dfxy by dy. Okay, if I have any point here, there is two components. One is x1 component and one is x2 component. That is different. That is the position. Position of this has two components. One is derivative. Derivative again has two components. This component and this component. Okay. Now if I have something like this, then if I combine together, then it will form a resultant vector. That is called derivative vector. Consider this on x-axis, dfxy by dx is 1, constant 1. Okay, how it can happen? Consider there is a fxy called x plus y square. There is a fxy surface called x plus y square. dfxy by dx will be 1. dfxy by dy will be 2y. Means in this direction height is changing as 2y. Whatever the y is, the height change will be more. If here y is 10, then here 1 unit change will change 20 unit in the height, very high, whereas x component is always constant whatsoever. This proves that if y is less, then dfxy by dx will be small. If y is more, dfxy by dy will be high, because dfxy by dy is 2y. dfxy by dx will always be 1. Makes sense? If I take these two vectors, from this vector and from this vector, and if I try to draw a resultant vector, then it will pass in between. This is dfxy by dx vector, this is dfxy by dy vector, then the resultant vector will be passed in between. What is the importance of resultant vector? There is no importance of resultant vector. Actually, derivative is in two components. If someone is curious, then he can draw a resulting vector. Resulting vector at this point will be different, this point will be different, this point will be different. Because if you go in the high y, then y factor will start growing. because it is 2y, whereas x factor is always 1. Means here resulting vector will be like this. Here slowly resulting vector will start moving up because y is growing. Makes sense? Slowly it will start moving up. If y is decreasing, then it will start going like this. If I am at a point called 0.1, 1, then y factor will be 0.2 and x factor will be 1. Gradient vector will be more or less along x-axis. But as we go up, gradient vector will start moving toward y. Means every point gradient vector is different. What is gradient descent algorithm say? Gradient descent algorithm say if you are at any point and then you have dfxy by dx and dfxy by dy, a resultant vector, that is dfxy by dxi plus dfxy by dyj, that is a resultant vector. Take negative of it. If your resultant vector is going in this direction, then negative vector will go in this direction. So if you're trying to find a minima from this point and minima is here, you have to proceed in negative direction of the gradient. Okay, and then you find another point. From that point, because if you move like this, constantly thinking that it will go to the minimum point, then every moment gradient vector is changing. That is the concern. What is the best way? One thing is that we have already calculated. Please watch our previous video. One thing that we have already calculated, that at any point I have a gradient vector. Any point. If I have a gradient vector at any point, then gradient vector will go toward the negative of the gradient vector will move toward the steepest descent, and positive of the gradient vector will move toward the steepest ascent. Make sense? Okay, I'll try again. Consider this is a mountain. This is a mountain. Okay, this is a 3D mountain. This is a 3D mountain. Okay, now mountain is like this. Okay, mountain is like this. Now at this point, if someone is thinking where is the peak, understand? A person is standing here in the mountain and then he is trying to assess that where is the peak, because he has to rise to the peak. What he will do? Understand? Peak he is not able to see. See, he is standing here. He is seeing in this direction. He is not able to see where is the peak of the mountain. He is standing here. How he can estimate that where is the peak? What he will do? He will see the bottom and he can see x-axis and y-axis. Now he will try to find how much is the change in the height along x-axis. How much is the change in the height along y-axis? Then he will draw a resultant vector. Understand? This is a very priceless discussion, not available in any of the book. If this is xy plane, then the person is standing here. From there, he will draw a straight line on xy plane. Consider it is hitting this point. Then along x-axis, how much change in the height he can see. And along y-axis, how much change in the height he can see. Whatever he can see, then he will draw a resultant vector. If this is a resultant vector, then wherever he is standing, he will see down the line one resultant vector and he will start climbing in this direction. This is called climbing up in the xy plane on the gradient vector direction. And that is called steepest climb. Now he is sure, at that moment he is sure that he is going in steepest direction. Okay, but probably this is not the way, because he has to go like this. Okay, so every moment he is walking, every moment he is calculating gradient vector, every moment. Because gradient vector will keep changing point to point. And wherever gradient vector is showing the direction, he is climbing. So if this is 3D, okay, if this is 3D, I have a very bigger 3D. So okay, so if he is climbing like this, so if this is 3D and person is here and he is to go up, at this point he will see the bottom and he will try to calculate the gradient vector on the xy plane. In that direction he will climb. So if he is here, probably he will go like this for some time. Then he will again draw a gradient vector and then he will see the direction. Then he will go like this. Again he will see the gradient vector, and then he will go along then he will go like this. Slowly he will reach the maximum. Every moment gradient vector direction is different. If he is moving toward the gradient vector direction, then he will reach the maximum. If he is moving opposite to the gradient vector direction, then he will reach the minimum. This is the algorithm, and that is called gradient descent. Gradient descent means negative. He will travel in the negative side of the gradient vector. If this is the gradient vector, at this point, if this is the gradient vector, then he has to travel this side to come to the minimum. If this is gradient vector, then he has to travel this side to come to the maximum. Okay, if he start moving in the negative of the gradient vector, keep doing every point he has to calculate again, because every moment gradient vector is different, and slowly he will reach the minimum. Okay, we are in discussion of what is the pitfall. This is very perfect algorithm. So if I am at any point x0 and I am trying to find next point x1 to have to come to the next step, because every moment gradient vector is changing, every moment direction is changing to come to the minimum. Is it understandable? Now he cannot walk too much. If he walks too much, then probably if he calculate a gradient vector at x0 and he is thinking wherever negative of the gradient vector he is walking on the hill, then he will reach minima. Then if he walks for long distance, then probably minima is here, and minima is here. Minima is here. At that moment, it shows gradient vector here. So every moment, if he calculate, the gradient vector will keep changing and he will come to minimum. Every moment he cannot calculate how far he will travel in the gradient vector. One question, and then he will recalculate it. Then he will calculate gradient vector and how far he can travel. Then he will recalculate it. How far he will travel? How far he will travel? Okay, so what if this is x0? Then what is x1? Next point. x1 equal to x0 as a vector plus and then negative of the gradient vector, because it will take it to minimum. Makes sense? How far he will travel? Okay, if I say gradient vector as only the direction, then I have to take a unit vector of the gradient. Now gradient vector is ready to give the direction only. If I multiply this unit vector with alpha, then how much distance I will travel? If you take big alpha, then you will start meandering. If you take very small alpha, then too many calculations are required. It will be perfect. What will be the optimum one? Anyway, if we settle it down, it will become x1 equal to x0 plus alpha into unit vector of the negative gradient vector. Unit vector means dfxy by dxi vector plus dfxy by dyj vector divided by the magnitude of the unit vector. Magnitude and alpha together, I can say alpha. Just alpha. Means equation is x1 equal to x0 minus alpha gradient vector. Every time you have to keep changing. Alpha should be small enough, so that every moment you calculate and you will have a better direction to reach the minimum. It should be big enough that you should go little distance. Otherwise, you should not keep calculating. What is the pitfall for this? There are two pitfalls that we have described. What is the pitfall for this? Okay, if I see consider this is xy plane. On the xy plane, consider the 3D shape is like this. This is paraboloid. 3D shape is like this. This is paraboloid. Okay, this is not I'm not talking about paraboloid, but this is paraboloid. What is the equation of paraboloid? X square plus y square. That is the equation of paraboloid. fxy equal to x square plus y square is the equation of paraboloid. What is equation of the other shape? The square root of radius square minus x square minus y square is the equation of a sphere. Makes sense? There can be another equation as fxy is equal to x square plus y, just x square plus y. dfxy by dx is 2x, dfxy by dy is 1. Means this shows that x square plus y means the change in the height along x-axis is growing if I move along x-axis like this. See the change in the slope. Here slope is this and slope is growing. But slope along y direction, it is not changing. It is always constant. Someone can imagine it. Or the equation of fxy is x square plus some constant. dfxy by dx is 2x. dfxy by dy is 0. There is no change in the y direction is seen. This will make a curve like this. Now, if I am at any point here as x0, and if I try to calculate the gradient vector will go negative of the gradient vector. If gradient vector is like this, because it has only x component, negative will go this direction. If I have taken a big alpha, then it will hit this side. There, this is origin, then it will go. Negative of gradient will go like this. It will start oscillating like this. It will take a lot of time to reach here. Makes sense? This is one scenario. Another scenario is considered that to reach the minima, we have a saddle. This is called saddle point. See, we came like this and came like this again down. If we have a saddle point like this equation, and if I'm traveling like this, if I reach here, then x component of the derivative is very less. Y component of derivative is again very less. Because it is a plane area. If it is a plane area, then dfx by dx is 0 more or less. dfx by dy is 0 more or less. If I multiply with alpha also, there is no movement I see here. If there is no movement I see here, x1 and x2 will be very little distance. Means it will take infinite moment, infinite iteration to cross this saddle point. These are the two problems of the gradient descent. Okay. Today finally we have covered it. Now we will proceed upon it. So gradient descent formula is to find the minimum point is xk equal to xk minus 1 minus alpha gradient vector. Okay, these are the two problems. How we can tackle it, that we will talk. We will talk in a theory called Newton's rule. So probably we will consider that. Please don't mind supporting us. +9 in the country code 94831 60610 is the telephone number. +9 in the country code 94831 60610 is the telephone number.